In this video, we are going to talk about some applications of double integrals. So first, let's say that I'm looking at the double integral of just dA. That technically means there's a 1 here, and it turns out that this gives us the area of that region R. Just to connect this to another idea that we've seen when we've looked at the line integral over some curve of just 1 ds. Remember that what that told us was kind of a measure of the curve, how long the curve was. So this was the arc length. The arc length. So in the same sort of way, when you do the double integral of just 1, it gives you a measure of this region R, which would be the area of R. So if I were to draw a picture, if I draw my axes, the x and y axes, R might be some region in the xy plane. It turns out this is true whether it's a rectangle or some more general region. Okay, so next up, what if I have the double integral of just some general function? It turns out that this is the volume. It's the volume under the graph of z equals f of x comma y. That'll be some surface in three-dimensional space. And above the region R drawn on the xy plane. So it's the volume of this solid. If we want to be more precise, this is actually what's called a signed volume. So when our surface is above the xy plane, it contributes a positive volume. But if it had dropped below the xy plane, it would have given us a negative volume. Okay, so next up, what if I'm doing a double integral over my region R of a density function? We saw this in our first video of this section. This is the mass. It gives us the mass of a two-dimensional flat plate. There's one typo here. Flat shouldn't have an E at the end. Flat plate with this density function, rho of x comma y. We can also write formulas for the center of mass. So the center of mass of a two-dimensional, also a typo there, so no E here. So for the center of mass, for the x coordinate of the center of mass, we are going to get a fraction. And it's very similar to what we saw before for the center of mass of a curved wire. We are going to get, in this case, a double integral over my region R. And then you take x, multiply that by the density, rho of x comma y. And then because it's a double integral, I write dA. All over on the bottom, I have my integral, double integral over R, of just the density, rho of x comma y, dA. Remember that this integral at the bottom, this represents the mass. Whoops. This represents the mass. For the y-coordinate of center of mass, it's a really similar formula. It's just this x in the numerator changes to a y. Okay. Next up, we have the centroid. So the centroid of a two-dimensional flat plate. Another extra E there that shouldn't be there. Remember, that's the center of mass when our density function is a constant. So I'll call it k, where k is a constant. So if k is constant, let's go ahead and work out one of these. If I plug that in here, I'll get my double integral over my region, y times k, the density is k, and then dA all over double integral over my region R. The density is k, and then I have that dA. Because k is a constant, we can factor it out of both of these integrals. So I can factor out the k, multiply my double integral of y dA. And then on the denominator, same thing. I can factor the k out times the double integral over r, and then I just have dA. Or technically there's a 1 here. But I notice these k's, now that they're factored out, they can cancel. And that gives me this formula that we have here. There's a very similar formula for the x-coordinate. We are going to get a fraction where on the top I do my double integral over r, and it's going to be x dA over double integral over r on the bottom of just dA. Or I could write that as 1 dA. So that's my formula for the centroid when the density is constant. This term on the denominator this represents the area. This is the area of the region. Okay, so the last application is what's called the average value of our function on our region. So we've seen a formula for this before in a different context. Visually, what the average value is if I go to my graph, it's kind of the average height in a sense. So it's like the height that I would need to reach, where if I make in this case, a solid box at that height, so I make a solid box over this region R, I need the volume of this box to match the volume underneath this curve. So this height that I get to, that should be this average value. So, okay, if I want those two volumes to be equal, let's write that down. I'd want the volume of our solid to be equal to the volume of that rectangular box. And for the volume of the box, we just take the height, which is F average, multiplied by the area of the base. So the area of that rectangle R. And then I can isolate for this F average by dividing the area of R. So our F average would be equal to the volume of our solid divided by the area of that rectangle, base rectangle R. And then what's the volume of the solid? Well, the volume of the solid is the double, draw mode, is the double integral over my region of our function, f of x comma y. And then I get dA. And on the bottom, the area of R, well, that's just the double integral over R. And then I could just write dA, or I could also write 1 dA. And that's my formula for the average value of a function. So in terms of our goals for the section, we finished our last goal, talking about applications of double integrals. In the next video, we are going to do some more examples of evaluating double integrals.